Okay, so thank you. Um, so I start with a few slides, just a couple of slides, and then it will be mainly on the blackboard. The reason I show these slides is because this workshop is mainly on new physics and galaxy clustering. I will not talk too much about new physics in the rest of the talk, so I'd like at least to motivate what is my approach to new physics and galaxy clustering and why I'm doing the more technical thing that I will talk about. So the idea is, again, like in the standard model of particle physics, we don't know which kind of new physics is there, if any. So a way to present that everybody knows in the particle physics community is to parameterize deviations from the standard model of particle physics via some symmetry-based approaches, symmetry-based parameterization, and to express the information about possible deviations from the standard model with this kind of plots. All of this, these epsilons are basically measuring the deviations in radiative correction, so that is beyond the linear theory from the standard model. And if any of these epsilon is different from zero, you have some deviation, detected some deviation. You don't know which model, then you can map your favorite model, but this is the way it is presented. You know, nowadays, constraints are at the per mil level in the standard model. So I would advocate a similar approach for the large-scale structure. The idea, again, is to parameterize deviations from lambda CDM, which is our baseline, in the most general way compatible with some symmetries. And the symmetries I have in mind are the equivalence principle, rotational invariance, something very, very, very general. You can do it, and you can define these epsilon parameters. And also, as for the standard model, you have deviations, in this case, also at the linear level. This is a fractional deviation in the growth factor, and but also on the nonlinear term. So this is the first non-trivial epsilon that you can have in radiative correction, that is second order correction in perturbation theory. And so the idea is some point to present, for instance, Euclid data in this way. And you see, okay, you have the epsilon f direction, which again parameterizes different models, but you also have another direction, open a direction in the nonlinear on the nonlinear corrections, which can help you disentangle different models of new physics. Okay. So what are we now? This is what we can do on these epsilons with Bose data. So this is a work in progress driven by Marco Marinucci and Giorgio Piselli. So you see, okay, I will not go into any details, but present constraints are around 20% on F and 90% on this nonlinear correction. So we are very far from the standard model state of the art, but this is what it is. And then we want to go in the future, maybe, which is analyzed in the so-called PT challenge simulation, with a simulation with the enormous volume, which is around 10 times the volume of Bose. But this is just to say what an ideal survey could possibly give you. You see, you pass from, how was it, 20 to 6% on F, and from 90 to 50%. This is with a state-of-the-art P plus B analysis. So the question now, and also the motivation of the rest of the talk, is can we do better than P plus B? P plus B are 2 and 3 point correlators. Are there any other ways, other ways to compress the data that you have and to extract possibly more information? Okay. If you have questions, please ask Marco. But so, having said that, I will now discuss the possibility to extract information from the field itself. The overdensity field itself, delta D. In the future, I mean, in this talk, it will be the density field for galaxies, whatever. And the idea, I don't compute correlators, but I really want to extract all the possible information from the field without any compression. So the thing to do, if you want to do cosmological inference, is to compute a field level likelihood. And this will be basically the topic of this talk, but I would like to do it in perturbation theory. And try to see what we are doing. I mean, what kind of things are we computing in perturbation theory when we compute this field level likelihood? So the outline of the talk, if you want, I will introduce the field level likelihood, and I will just review some previous results and some previous approaches, and then I will do a fully perturbative computation for the field level likelihood, including noise, and also including a generic value for the cutoff of the theory. I will discuss it in the future and later. So in particular, I will I will allow the cutoff of the theory with which I compute the model to be larger than the Kmax. Kmax will be related to the data. Lambda view will be related to the theory, if you want, is the cutoff of the initial field that go into the computation when I compute loops. Okay, and then I will present some way to compute this guy by doing some expansion in correlators, and I will discuss the relation between this expansion and the perturbative expansion, which are not one-to-one. And finally, if there is time, I will also show how, with this setup, I can construct, I can, if you want, reconstruct the initial field. That is to say, I will define some classical initial field, which is the best possible value for the initial field, given the data and given the noise. Okay. Okay, so if there are questions or comments or remarks, please tell me at any time. So I'm very happy because all the experts are here. So I will just review some initial papers by Fabian. Okay, Fabian wrote a lot of papers on this. I just quote a couple of them. Et al. And also Cabas, Schmidt. So this one is from the first one from 2018. And this one is from 19, which they basically derive the field level likelihood. So how can you write the field level likelihood? So basically I have some data field, and I want to derive what is the probability of this data given a model, given a model for the initial conditions and a model for the noise. So basically the idea is quite straightforward. So I assume to have a model which gives me a fair representation of the data up to some Kmax. So I call it this delta bar, and this will be a functional of the initial field and all of the noise. I will not be more specific at this epoch. So if you have an initial field configuration and the noise configuration, then your final data will be just, the probability of your final data will be just a functional delta function, which tells you how these initial conditions with this noise evolve down to the data. So this is, okay, one part of the problem. You have to derive this forward model. But then in cosmology, we never have this problem because we don't know the initial condition and we don't know which is the realization of the noise. So what we do actually is a functional integral over the initial field and over the noise field with some probability distribution for both of them. Let me very generic here. I will call it representative this way. So this is the, if you want, the task. You want to compute this guy in such a way to analyze your data once the configuration that God has given us is measured. Okay, this, if you can check trivially that this likelihood is normalized to 1 if this guy is normalized to 1. And then you see what are the ingredients. So the first one is the forward model, as we said. It also depends on some the number of parameters which are cosmological and maybe nuisance parameters if you have bias tracers. Then you have to know or assume the statistics of the initial condition. This is again part of the model. This can also depend on parameters. And then, if you want to do the whole thing, you have to marginalize over the initial conditions and over the noise realization. Okay? So let's analyze things one by one. So the forward model. It can be any forward, in principle, any forward model you trust. That is, it can be simulations, for instance, like these people, Borg, for instance, are doing, Yash and other people. But in this talk, I will focus with on perturbation theory. So I will consider in perturbation theory forward models. And in particular, but this, I mean, I will give a general framework, and then you can plug your model, your preferred model, your favorite model. To fix the ideas, I will use the effective field theory of large-scale structure, which includes perturbation theory expansion for the matter density field, bias trace, bias coefficients, noise, and whatever. But you can also have, for instance, LPT plus bias. This can also be done perturbatively. And so the idea is to you use some analytical expression for the forward model, which will be by force truncated at some level of the approximation. Okay. So in my case, it means that the forward model, just to fix the idea for everybody, will have the expression of some convolution over initial fields where I integrate over all the repeated momenta here, plus some noise, which I assume here to be additive. Again, it's not, I mean, you give me a forward model, as you see, we will see, you can compute L, but in general, this is, of course, a simplified assumption, which is true most of the time, but it's not necessary here. But just to fix the idea, we'll use this one. These are the EFT of large-scale structure kernels. You can find them everywhere. Sorry, this is just delta 1 of P1, delta in of Pn, and powers of the linear field. Okay. Statistics of the initial condition. Again, in general, can be anything, but if you want to compute something, you have to do some assumptions. Okay. An assumption which is well motivated is that it is factorized, and these are just Gaussian initial conditions, if you want. So it's something like delta in square divided by 2 power spectrum plus volume logarithm of the initial power spectrum. Okay. And again, this is not necessary, but you can also assume that the noise is Gaussian distributed. I just write it P noise of epsilon plus. So basically, the initial statistics in this case of Gaussian uncorrelated initial condition is just defined by the initial power spectrum and the power spectrum of the noise. Okay. So if you have this condition, if the power spectrum of the noise is Gaussian, sorry, the probability distribution of the noise is Gaussian, then you see that, and if the noise is additive, then you can see that part of this integral is trivial, because I can integrate over the epsilon here, and here I have a plus epsilon. So basically what I get is that my likelihood will be just proportional delta theta minus delta forward model, which depends now only on the initial field, modulo squared divided by 2 times the power spectrum of the noise. Okay. Okay, this is already something, because with with this part of the likelihood, that is to say, if you want the likelihood without marginalizing of the initial condition, say condition to some initial conditions, I can do already some tests. For instance, I can test my forward model, up to which order in perturbation theory I have to go if I want to go to some Kmax, and also more subtle thing like the dependence of the ultraviolet cutoff of your theory. Now you have to compute this forward model on some grid, because you want really to evolve the whole field, so you do it on a lattice. This lattice will have some ultraviolet cutoff, and then of course you want that your theory predictions for physical quantities are independent of this cutoff. This is just a renormalization, but you can test renormalization for the parameters that you want to measure, up to which order you have to include counter terms and these things. There was some work recently about, again, these bootstrap parameters by a student of me, Takahiro Nishimichi, and Atsushi Taruya. We discussed precisely this for a model with for a model with fixed initial conditions. Okay. Sì. Sorry. Yeah. Basically, when I compute this delta in, this initial field. I cut off it at some ultraviolet scale, which corresponds roughly to the grid scale of the theory. And this, in general, this cutoff, lambda UV, is different, is larger than the cutoff K max on which I trust my data. Okay, so yes, sorry, this goes up to K max, but if you want the convolutions, the perturbative convolutions with which I obtain delta up to K max, here I have integrals done up to lambda UV. Okay. And of course, I mean, theory, I mean, prediction should be independent on lambda UV. Okay, but this is, let's say, not the easy part because there are already a lot of non-trivial things here. But my focus here will be on part 3, that is marginalization over the initial conditions. So, 3. The problem, as you can understand, is, I mean, if you want to address it from a numerical point of view, which people like Fabian has done, for instance. No, for instance, not many people. Then, okay, you have a lot of parameters. I mean, if you have like 1 gigaparsec cube volume, and you want to go up to lambda UV of order 0.3, h over inverse megaparsec, then you can count easily like 10 to the 5th parameters into the 5th amplitudes and phases for delta in to marginalize over. Okay, so you can do it. You can try to do it numerically. So there are order 10 to the 5th parameters, and then of course there are all the cosmological and Nuisance parameters. And to do it, I'm not an expert at all, but I know that there are experts in the room. You can do, for instance, this Hamiltonian Monte Carlo or microcanonical Monte Carlo, this kind of approaches. Okay, I will not touch on these implementations. Of course, I just say that this is possible, and this has already been applied to analysis on simulations. So again, Fabian has tried to extract the amplitude of the initial power spectrum from an analysis of halos, and he found very good constraints from the field level on this amplitude, much better than the P plus B. I know that there are other papers like Marco, and Francesco Speziati have also analyzed this thing from a perturbative point of view. But just to say, this can be done. So my point of view is to, if you want to understand what you are doing when you are doing this numerical, non-perturbative, if you want, marginalization. So if you want, my point of view is more simplistic. I have a perturbative forward model. I have to do a marginalization. Why don't do a perturbative marginalization instead of doing a non-perturbative normalization? At the end of the day, we already trust perturbation theory for the forward model. So this is just to derive a tool to do this, including, as I was saying, noise and lifting this, I mean, allowing lambda UV to be any value. And then with this, of course, you can compare with principle with the result of a numerical marginalization. You can set benchmarks and so on and so forth. So about perturbative normalization, there are already, as far as I know, at least 2 papers, very good, very interesting papers. One is by Cabas, again Marco, and Matthias. It is from 23, and there is a more recent one by Fabian again. I think it's this year. Okay. So I just sketch you how it works in this case, and so you can then compare with what I'm doing. So to derive this perturbative generalization, correct me if I am missing something, they do two assumptions. The first one is the noiseless limit, which means that if you want your noise power spectrum, which if you can think it as proportional to 1 over the density of your traces, goes to 0. So if you have a Gaussian distribution and the noise goes to 0, it becomes a delta function. So it means that Pn of epsilon can be approximated by a functional delta function. Which simplifies, of course, the functional integral a lot. And then you will understand why in a second. Basically, they assume, or they work in the limit in which lambda uv is equal to lambda to k max. That is to say, they have the same wave numbers in the data and the initial fields. So why is that? Why is that? What can I do? But basically, I have to cancel something. Yeah, please. And then how do you invert the perturbation theory? Yeah, but I mean, if you want to do it numerically, no, you have a given wave numbers in delta phi. So this is what. Ah, okay. Of loops, if you. No, no, please. It's a key point. So please. Yeah, but how? I mean, if you don't know delta d up to k infinity, how can you invert? No. Yeah, the inverse model. The UV is for me is the cutoff on the initial field. Maybe this was okay. So here I missed a part here. So this is the initial delta in. So you see that I mean it's quite trivial here now. If this becomes a delta function, I can basically do this. Maybe let me write it here. I can do this. This path integral basically analytically. So I have now, I just rewrite it. Then I have a Gaussian initial conditions for delta in. And then I have a delta function, delta data minus the forward model, just the deterministic part of the forward model, the one without noise. Now this delta comes from the noiseless limit of the Gaussian. Now you see, I basically change integration variable here, and so basically I can do now the integral, and the integral is given by I have a Jacobian to the -1 probably, and then I have -1/2 delta in of delta bar, say square, where everything is computed in delta bar equal to the data. So you see, if I know the forward model, I can compute this Jacobian, and I also have to know the inverse forward model, so I have to know also delta in over delta bar, if you want. So this is the inverse. So what are the initial conditions related to a given set of data? I can do it perturbatively. I can do inverse PT. And then I can expand perturbatively in the initial, in the data delta bar, both this one and this one. I get a series which gives me the perturbative expression of this likelihood. Okay. Okay, now my point of view is to derive the same, similar thing, but without these two restrictions. And okay, my original purpose, now I'm less optimistic, is to use it for real inferences, if you want, without going to this Hamiltonian Monte Carlo numerical marginalization. No, I'm not less optimistic. I didn't think about it too much. But then also, once you have this tool, you can compare numerical, a full non-perturbative marginalization with the perturbative one, again, including lifting these two restrictions, and try to learn something about what you are doing actually when you are computing this this field level likelihood. The initial field, yes. The initial field is Gaussian, but this relation here is non-Gaussian, non-linear, of course. Which comes from the inverse kernel. Yeah. So what you derive exactly is a series expansion in kernels times kernels times delta products of delta data fields. Okay. I will do the same computation. I'm not saying that this is wrong, of course, this is perfectly true. I will do the same computation, but just to see what is model and what is data. Okay, just to. This is what we were discussing before, no? I need an inverse model. So imagine you want to do it numerically. You have a given number of wave numbers here, and if you want to have this inversion working, you have to have the same wave numbers in the initial fields. So lambda UV is the maximum wave numbers in the initial fields, and K max is the maximum. Okay. Which, if you work at tree level, of course, there is no point, but then if you're starting to include loop corrections, quantitatively could matter or not, but it should be possible to do it. Yes? Exactly, this is exactly field theory. It's like a Wilsonian field theory, no? No, you have to, exactly, yeah, you have to check it either analytically or numerically that your results are, you are absorbing, you have counter terms, which basically take into account all the modes above the cutoff up to infinity, and then you have to check that your computation is independent on the physical quantities on this cutoff. For instance, okay, we got very sensitive on this because of these bootstrap parameters. No? Normally, you have bias parameters which are non-physical. So in any case, if you have some cutoff dependence, you can always absorb them in the bias parameters, but these booster parameters, we want them to be physical, so cutoff independent. So for instance, in that case that I was discussing before, to measure the booster parameters accurately in a lambda independent way, you have to go up to 5th order in perturbation theory, because there are some two-loop effects which are important. Okay, so the starting point is of course the same. So it's already here. Let me do an armless operation, which is to split this this delta function as follows. It's not really necessary, but since I mean I would like to separate model and data, so what I do is I introduce a model, if you want, field, and of course I integrate now over the model. So of course this is exactly the same. Sorry, delta m. This is exactly the same expression that I've written before, but I will use it because now I give a functional representation of this delta function with some integral over some field JF. Okay, so this is this delta function. JF is a new auxiliary field on which I integrate. And so in this way, now I can factor out the exponent. You see that this just becomes the integral over JF over I JF delta D times some functional of JF at all alone. No, sorry, yeah, some function of JF. So this is just what like I like field theory. Like I want to put it in a way which is in a form which is closer to field theory. So what is Z? Well, this is nothing but the integral over the model field. Well, let me write it this way first. Some distribution function of the model, and the distribution function of the model is again the integral of the initial field, the noise of all this stuff here. Okay, so but in this way, okay, I did nothing, but I factor out the two problems. I mean, everything which is in the model is here. Model. This is just the generating functional of correlators of the model with the distribution function of the model. And so the recipe is simple. You have to compute this generating functional with a finite value of the source, which is different what we do usually in field theory. And this is important to be finite, because then your likelihood is just the functional Fourier transform of this guy with respect to the data exponent. Okay, so now the approach is compute this. When I say I compute it in perturbation theory, I mean perturbation theory of the model. So I have I have to assume some forward model up to some order, and I want to compute this Z at the same order in perturbation theory, and then take the Fourier transform. Now, at least formally, everything, I mean, all this, the initial noise, lambda UV, no, Kmax is here, so the initial noise, all the parameters, lambda UV, are on this Z, okay? And don't have to make any approximation for the following about like 1 and 2. So just look at, let's have a look, a closer look to this Z. Again, Z in 0 is just 1. It's just a normalization of the full distribution function for the model. and then the first derivative with respect to JF, JF equal to 0 is 0. So if now I will do an expansion in powers of JF, and this is not the only thing I can do, but I will try these things. The expansion starts at second order, but actually I will not work on JF, on Z, because Z is a generating functional of the endpoint correlation function. I want the generating function of the connected endpoint correlators as usual. So I will define, as usual, its logarithm. Up to now, it's just, very simple thing. And now I will expand this in powers of JF. So the first term is just a quadratic term, where now here I have the 2-point correlation function of the model. It's not the 3 level, it's completely, non-perturbative. All the loops for the 2-point correlation functions. And then all the rest, I call it some, say, interaction or non-quadratic part of the action, which, if you want, I can write it as some sum starting from 3 of, now there are some i's, and I have, okay, convolution. Okay. Okay. So my model will give me my model at a given order of truncation will give me W2, Wn up to some order. Once I have computed them, I have to do the Fourier transform. But the Fourier transform, you can do it with the usual trick. Say some n. So basically what I do, I take this exponential part and I take it out of the integral as usual by taking the derivative with respect to the delta field. And what remains is just the quadratic part, that exponent, which I can do it analytically, so I will call it the Gaussian part of delta D, where again, Gaussian here means that it is quadratic in delta D, but it contains, again, higher order terms in W2, like the 1 loop, 2 loop power spectrum, so on and so forth. And this one, of course, I can integrate. Now I skip a little bit some of the, so this is delta D square divided by delta V2 minus, again, the trace of the log of V2. So just to say, this is something that I can compute analytically. It's inside the, exactly. So you give me your forward model, your UV, you compute these guys. Yes. So you have this expression for Z. And then what remains to be done, this Fourier transform, as you see it, is a series of derivatives of the Gaussian part. So here, if you want, I have the exponent. The exponent is this one, where each one of these sources become a derivative with respect of delta D of the Gaussian part. Okay, so now the procedure, at least the one at the time following. No, the W2 is a 2-point correlation function, and then it depends on your model. If it is a 3-level model, it's just the linear part. If you go up to third order, it's 1 loop. So you can, so this is such a good point, because then you can expand also this guy around the zero part. So you have non-linear contributions coming also from these guys, which are crucial. Otherwise, you get biased when you go, for instance, at the second order. I will try to show it. So, how much time do I have? 10 minutes. Okay, just very quickly. Then, if you want, we can discuss in private. So let's do the simplest thing. Let's go to zeroth order. So I'm using a different counting than everybody else. For normal people, linear theory is first order. For me, it's zero order. So because it's, I mean, for me, it's simple to count the number of nonlinearities. Basically, now I count the number of interactions. Okay, just add one, and then you get the normal counting. So, so you have to assume a forward model. Assume a zero order forward model, which means my model is just, let's say, and just to simplify things, just to show how the things are working, I will just use two parameters, B1 and A, where A is the amplitude. All the rest is fixed to the fiducial, otherwise I have too much complicated equations. So my model is simply B1A, say delta 0, plus some noise, okay? Delta 0 is basically the initial field multiplied by the initial growth factor, okay? It's nothing. So with this model, I can only compute W2, okay? The only non-trivial, non-zero, non-trivial correlator is W2. P epsilon of K, let's call it. And then all the Wn's are 0 for n bigger or larger, so larger than equal to 2 to 3. So I just go very quickly because the result is, of course, what one could probably expect. So with this, you can compute, you see, all this part is 0 now. Here you just have this Gaussian part with the linear power spectrum. Maybe I can skip a little bit. So if you take now, well, let me say two things. One, if you take now the logarithm of LG and you compute the derivative with respect to A, which now I want to measure A, for instance, the amplitude, then you get that it is, of course, proportional to B1 square A square minus the fiducial value of both. Here there is an assumption that when I take delta data, the average, this is just the volume times the fiducial power spectrum. Fiducial is B1 equal B1 bar, A equal to 1, P0 plus P epsilon. So, okay, you get, of course, there is the usual degeneracies between B1 and A, but you are unbiased on the fiducial. And then the second part, you can compute now the error on A from this simple setup by taking the second derivative. And what you get is a sum over wave numbers of 1 divided by 1 plus P epsilon. Now I discretized everything, so the integral becomes sum over wave numbers, and you get B1 bar square power spectrum square. Okay, this is my result. So you see, in the noiseless limit, the limit in which noise is 0, this is just counting the number of pixels that you have. So the result is the number of pixels, but it is less of that if you have a noise, because noisy beams, of course, contribute less to your error. This is just a trivial check to see that at least at linear order we are doing well. Then you can go at first order, so first order, I cancel the most important part. So basically, you have to take the okay. So first order, it means that my model now is this D0 plus D1, where this D1 is just this kernel that I wrote, the second order kernel convoluted with the linear fields. And so with this model, I can compute, of course, again, W2 at zeroth order, but I can also compute W3 at first order, which has the usual expression, Q A square K2 power spectrum plus 2 permutation. Okay. So how does it look like at first order? So now the first correction to lambda d is minus 1 cube, 3 factorial, 3 functional derivatives of the Gaussian part. So what you get is minus 1 cube, 3 factorial, the convolution of W3, zeroth order, power spectrum, with the 3 momenta P1, P2, and P3, and delta D, P1, delta D, P2, delta D, P3, everything multiplied by the Gaussian part. Okay, there are integrals and so on and so forth. So I can. So this is then LG zeroth order times what I call delta L1, which is this part here, and I can give a graphical representation in this term. So basically, it's a 3-point function of the model times 3 fields of the data. So each one of these is a delta field divided by W2, and this is W3 of the model at linear order. Okay. Now, first important thing, interesting thing is that if you now try to compute the derivative with respect to A of this guy, the average of it, then you get biased. You see that there is a non-zero contribution, because basically this one is cancelled by nothing else at this order. So what you see is that if you want to cancel this guy here, you have to expand your likelihood to second order. So there is a crosstalk between first order and second order corrections in the model, which is crucial, otherwise you don't have this cancellation. So what I mean basically is just if I have 1 plus delta L and I take the logarithm, so the logarithm of the likelihood contains not only delta L, but also minus 1/2 delta L square, delta L1 square. So this is formally a second order term. And then only if you consider also only the second order term, then the thing is biased if you have a non-zero bispectrum in the data. Let me just make maybe for discussion for the questions. One thing which is not clear to me at this point is the following. So when I do this, I compute, as you see, a convolution between the model bispectrum and the data bispectrum. Now, the data is defined up to some Kmax. And usually, I would like to take a Kmax of order I don't know, 0.10 or 0.12 for delta D, because this is where, for instance, one loop power spectrum works reasonably well. But then it means that also I'm trusting my model by spectrum at the same level of Kmax. Otherwise, I don't have this cancellation, for instance. So it's not clear to me. And I mean, normally, if you are familiar with this kind of analysis, for the 3-level by spectrum, I have a much lower Kmax. So I don't know why. I mean, why? This, I think, is an open question. If I do things, of course, at feed level, I'm just imposing Kmax once for all. But this means that I'm relying on this kind of cancellation between terms that in principle are in a region which I shouldn't trust. Finish, almost. Second order, I just give you. Do you define, I mean, you decide the value, or you do? So you are asking how the Kmax extracted in real analysis. This is what you. Yeah, yeah. No, I mean. Up to, I don't know, yeah. This is a Kmax. Now, my question is, how can we trust this Kmax, since we know that for bispectrum analysis, we should, and this kind of consideration that we are doing, we should stop at lower Kmax. This is a question. I mean, it's not clear. Maybe you have some more insight than me. Ciao. That I would like to. That I mean, I would agree with it. I mean, I've never done this kind of analysis with power. I mean, yeah, yeah. No, me personally, not you. I mean, the same Kmax. Yeah, but okay, maybe. I mean, there should be some explanation like that. I mean, the only thing, the only point I'm making here, you don't have the freedom here to choose different Kmax between power spectrum and bispectrum, because you just. Yeah. Exactly. Yeah, I know this argument. Probably you. Yeah. Could be interesting too. Yeah. The 5-point function. Yeah. There should be something like that. Yeah. I just sketched the second order because at least. So at second order now I have, if you want, 3 types of contributions from taking the derivative of the likelihood. So I have a contribution with 2 functional derivatives, where I have here the one loop part of the power spectrum. Then I have the tri-spectrum, which is the second order model. I simply add the second order kernel. So this is a tri-spectrum with 4 derivatives. And then I have the bispectrum square, cube. So now I take derivatives, and I don't write any formula. So basically what I have here is a one loop W2 times two linear fields. So this is, okay, this I can write. So this is one loop. So this is a one loop W2 times delta D square. Now, if you go and take the derivative, you see that this is biased. This is non-zero, of course, because there is just one term. There is no reason for it to be zero. Indeed, it is not. So this is what I was mentioning before previously. So here I have a contribution, I mean, of the order W2, 2, W2, 0 on the fiducial. So this is cancelled by, I was saying, as I was saying before, yeah, a second order correction to this quadratic part. So this has a 1/2 delta D W2 0 delta D, sorry. So it means that this delta D now is not linear, but it should be second order, exactly to cancel the guys here. No, sorry, I'm saying a stupid thing. So this is W, and I have to expand it as second order. No, sorry, okay. Again, so this is W2 here, and I have to take the one loop part of the power spectrum from here, and this cancels this guy here. Now here is the tri-spectrum, and I finish here. The tri-spectrum basically gives you two contributions. Tri-spectrum of the model times 4 times the delta D field, plus a one loop, if you want, in which two legs are closed on one loop, and second order. Okay? So I have a four order field and a second order field. I take the derivative. This is again, I mean, each one of them taken simply is singularly is non-zero, the derivative. I need both of them. But the other point is that this four-point function, I have to set to 0 the connected part. So what I mean is that this part goes to 0 only if I have no tri-spectrum. Or another way to say it, to be sensitive to the tri-spectrum in the data, I have to go to higher order in this expansion. Basically, I need to compute all terms in which I have tri-spectrum square here, which is a fourth order in my counting. And so if I just do a perturbative computation as I formulated it and I stop at second order, I'm not sensitive to the tri-spectrum in the data. And here there is a difference between this way of doing things and doing it non-perturbatively, because if you do it non-perturbatively, so basically in my expansion that I wrote before, you have all powers in the tri-spectrum, for instance, because it's just an exponential. So you have a model, forward model, in which you compute the tri-spectrum at 3 level, and then you do this numerical marginalization. Basically what you have, you are summing all orders in perturbation, I mean, all orders of powers in the tri-spectrum, but you don't have, for instance, the two-loop power spectrum or the one-loop bispectrum in your computation. So the question is if this is consistent or not. So I think I can stop here. I have, yeah, maybe I can talk if somebody too interested in the way to use this setup to derive the reconstructed field, which is nice, I think. And but as a general comment, again, I view this as a possible way, I mean, to at least to organize things that we are doing when we are doing a field level analysis, to compare or to benchmark with respect to numerical marginalization. And but the question remains open up to this point, at least to me. Is there more information in the field than in the power spectrum plus bus spectrum? I don't have an answer. Maybe once you have this expression, this general expression, then maybe the expansion that I did was not the most clever one. I mean, just expanding in powers of the source, which means in correlatos, especially if you want to go to extract information at small scales. Maybe another approach in which you are doing things not in Fourier, but in configuration space and looking for some shapes and these things can be more powerful. But at least, I mean, in this general setup, at the moment, I don't see the way to extract more information from the field than from correlators if you stop at the given ordering perturbation theory. That's all. That's all. Mm-hmm. Yes. Wow. Exactly. So this one contains also the noise power spectrum. So this is linear plus noise. But yeah, you are right. Yes. Yeah. I'm expanding in powers of correlators. So yeah. Hmm. Yeah. There's some. Yeah. No, no. Actually, it's a very good questions. I didn't think about it. Um, yeah, of course. What you have to do in this case is really to resum. I mean, to take seriously this exponential one, and probably to resum it. But yeah, I didn't try yet. But so my one question is, okay, it's true that you have different configuration, different correlators which are talking with the higher and lower orders, but there is also some kind of a segregation. For instance, W4 talks only with W4, W3 talks only with W3. I mean, in the sense that if you take that part of the likelihood, this is unbiased by itself. So maybe it points out to some kind of estimation that you can do without becoming biased. But these are just words for the moment. This is just very recent stuff. So, but yeah, your point is definitely correct. Are you talking about field level versus power spectrum, possible spectrum? Uh-huh. Mm-hmm. Ah, okay, but no, but then the point is, at what point in correlation function will you stop? Okay, theoretically, again, you can go to the fifth, seven, and so on, but from a practical point of view, maybe. Yeah, okay, if we stop in the same order, no, I agree. If I do things in this way, I expand in this way, so basically what already they found that I am also just rediscovering fresh water with noise, with some making some noise, is that, yeah, you basically have the same information. In my, yeah, you are talking about non-perturbative stuff. Yeah, yeah, that's the only hope I think you can. Well, yeah, I mean, if I do it with external, I mean, I need to keep the external sources switched on. Yeah, Leonardo, I agree. Yeah, okay, but then no, if yeah, if you just do a naive perturbative expansion as I did here, and you compare with a naive perturbative expansion of the power spectrum by spectrum and so on, I think that's it. My only hope is that with the field, if you go to, yeah, maybe to look for particular, I don't know, configuration shapes close to halos, you know, this. There are regions in which basically the single stem approximation is still valid, but it's very difficult for perturbation theory to catch up. No? Yeah, probably, maybe yes. Yeah, I don't know. Yeah. No, but I agree. I mean, if you do just Fourier space, no, I think it's a fair discussion. If you do just Fourier space, K max everywhere, just blindly, and then I think, yeah, there's not so much to play. This is why I was referring to configuration space as opposed to Fourier space, because I don't, I mean, you know, with this kind of statistics which try to capture some localized shapes like wavelets and so ever, or marked power spectrum, you get some, apparently some more signal, which is difficult to capture in perturbation. In a perturbative expansion truncated to say third order or fifth order, you cannot, will not go much beyond that. So you're saying that these ad hoc approaches, there are some, you want to understand which type of diagram? Exactly, yeah. Some kind of different statistics. The point with this new sum or different summer statistics is they're very difficult to model perturbatively or analytically. Yeah. Yeah, you have, yeah, you have. Well, in some cases, you know that you can resum classes of diagrams, no? Like, okay, you don't have time. If you do this, this reconstruction. So reconstructive field is basically, you can write down an equation which is an infinite sum of derivatives or correlators of between n late time field and one initial field. And you can have an infinite. You can see it clearly that there is a structure which, as usual in BAO reconstruction, when one of the momenta is much larger than the others, this resums at all orders. So in these special cases, you can do some resummation, but again, if you just Eulerian truncated second, third, fifth order, I think that's it.